So today we're going to look at reviewing atomic structure, electron configuration. I don't think this is a review. This might be new to you, is photoelectron spectroscopy. And that's going to give us some insight on where electron configuration and atomic structure come from. Okay. So definitely reviewing first year chem. This is our oldest model of the atom. And then really no definitive idea about what the atom is with Dalton. And then we move on to Thomson, and Thomson used the cathode ray tube to figure out that there were electrons. And if there's electrons, negatively charged electrons, there better be positive charge. He didn't explain the positive charge other than it's there, but it's a solid mass, and that's a very primitive model of the atom. And then his student Rutherford came along and tried to do some further experimentation to support Thomson's model, but when he did the gold foil experiment, and he shot radioactive source, it says here, but it is alpha particles. They are positively charged particles. And he shot this at a very, very, very thin gold foil. Most of the alpha particles went straight through. Occasionally they got deflected just slightly. Occasionally, very uncommon, but it did happen that they got deflected a lot more than just slightly. So what does that mean? Well, it means that this model of the atom by Thomson can't be correct. So it can't be a solid mass. It must be mostly empty space. So the Rutherford model is mostly empty space. Still has to have the same collection of positives and negatives. Still has to have the electrons from Thomson's model, but almost all the mass is going to be in that really tiny nucleus in the center of the atom, and it's going to be positively charged. So that model held up for a while, and then Bohr came along, and the main thing about Bohr's model, it explained how what's the nature of the electron. And so that looks like maybe planets going around the sun. And there are inner electrons and there are outer electrons. And that model worked out perfect when you used a spectroscope and looked at line emission spectrum. And you did this in first year chem, I think, or at least you talked about it. And these are wavelengths. By the way, there's another color there, but we can't see it very well. But those wavelengths worked out perfect for the energy that these electrons possess. And there was some math, we're going to get into this in a different day, but the speed of light equals wavelength times frequency. And also energy equals Planck's constant. We don't know about that yet. And multiplied by frequency. So that math worked out perfect when that's hydrogen. When mathematics were done with hydrogen, it worked out perfect, experimental and the theoretical. But that's not the model we like anymore, because other people tried to do other atoms, this experimental with the spectroscopes and theoretical with the math, and it didn't quite work out. So we're going to eventually get to other models of the atom. Well, one more model of the atom. So this is just a little rundown of some of the individuals that we just talked about. There's a few other ones in here. They're not going to be very important for AP chemistry. That doesn't mean they're not important. And again, here is our models of the atom. Oh, we got a new model. The electron cloud model. Some people call it the quantum mechanical model. Some people call it the Schrödinger model. It does go by a number of different names, but it certainly looks different from the Bohr model. So it has some ideas of the Bohr model. The electrons are in different lengths or radius or whatever you want to think about it, distance from the nucleus. But one thing that's different about them is we do not believe that they're revolving like planets around the sun. We're going to talk about probabilities, where we think electrons are going to reside. Okay, so we're going to get into that in a few minutes here. You might remember that these were, I don't teach this diagonal method, but this is a way to remember where all the electrons can reside from their closest to the nucleus until further away from the nucleus. And it's basically like snaking around here. 1s, 2s, 2p. I'm not going to continue this on forever, but that is, you keep snaking that through. It actually goes to infinity. This one just goes to 8s. And this is another way to look at it. You would start at the lowest energy possible, and electrons could reside in 1s. And then they could then, after 1s is full, then they could fill up 2s. And also you might notice that there's differences in distances. So there's big jumps between 1s and 2s, but then there's some places where the jumps are very small. And this, by the way, is not to scale. Some of these jumps are very, very, very small from one to the other, so small that there are times where electrons might reside in one of the spots that theoretically they shouldn't. But because the energy differences aren't that big, sometimes they do reside there. So we'll talk about that also. Okay, the Bohr model. We still like a lot of things about the Bohr model, and I already think I mentioned some of these already. But let's think about what we like in our new model that came from the Bohr model. So the electrons are attracted to the nucleus. Okay, so we didn't really talk too much that there's protons in there, but we now know that there's protons in the nucleus. They're going to reside in certain defined distances from the nucleus, further away, closer, so forth. And then this is an important point about absorbing energy or emitting energy. So if you have your nucleus here, and maybe we have and the Bohr model is still a nice model to use as far as writing, because you can show it two-dimensionally. And yes, we have a model that now we like better than the Bohr model, but it still serves a purpose, and especially for writing things like on a tablet here, makes a lot of sense to use the Bohr model. So if you would take this electron that's in this orbital and you would give it energy, you could heat it up, you could give it electrical energy, it would be able to go further away from the nucleus. At some point, just like if you threw a ball, gravity would act upon it. Well, the positive and negative attraction would act upon that electron, and it would fall back down. And when it fell back down, it would release energy. And that squiggly line is like my little frequency that would show you that there's light emitted. So when it falls back down to ground state, it releases energy. To get to excited state, you have to give it energy. And we'll probably talk about that a number of times. And I didn't mention this by law, but we're going to now mention it by law. This attraction of the nucleus and the electrons is governed by Coulomb's law. And if you look at this one here, this is a negative and a negative. Those two forces are going to repel each other. I think that's pretty obvious with magnets. And the same thing would occur if you have positive and positives. So that's not really what we're going to talk about with Coulomb's law. We're going to talk about the attraction of positives and negatives. And this attraction is governed for us. We're going to we'll call it F force. Sometimes we'll call it by different letters, but we can call it by force because that's what these guys called it here. And it's governed by a constant. And the constant's not going to do us any good because we're not going to use this mathematically. We're going to use this theoretically. But it's governed by a Q. And that Q is a charge, maybe the charge of a proton. And then another Q. And that Q is another different charge, like maybe the charge of an electron. So you would multiply those two together. Of course, again, we're using this theoretically, not mathematically. And then on the bottom is an r squared. To us, it doesn't matter if it's an r squared or an r, but r is radius. And radius is about distance. So if the distance is small, if the radius is small, that's going to make the force bigger because it's on the bottom of this fraction here. As opposed to if the Q's, any of the Q's are bigger, the force becomes bigger because they're on the top of the fraction. And then the opposite would be true. So if the distance is much bigger between the two charges, then the force is smaller. And this would work with magnets too. So if you would have a magnet you put right in your refrigerator, that would be, I think, really a small distance between the two. Actually, it'd be like touching, right? Well, if you would try to put a phone book between the magnet and the refrigerator, I don't think you're going to get that attraction to happen. Why? Because that radius, it's not really a radius, but we'll call it a distance between the magnet and the refrigerator is too big. So there wouldn't be an attraction there. And that Coulomb's law, we're going to end up using that for lots of things this year. We can use it for ionic compounds. We can use it for things about the electron. We can use things about the nucleus. We'll use that a number of times. Okay, so our last model, or our most current model, is the quantum mechanical model, the Schrodinger model. Again, it goes by a lot of different names. But this model does use data. So it's not just completely theoretical. It does use lots of data, actually. We're not going to go into a lot. We'll go into a little bit of the data. What we won't go into is any of the math. The math is definitely a calculus-based math that this class doesn't touch upon. You would get this in a class maybe called physical chemistry in college. You might touch upon it in a couple other different classes also. But Schrodinger put together some of this calculus that helps explain the nature of these electrons. And these electrons act kind of like particles, but they also kind of like work like waves. Waves are like energy. And this is a key term. So in the Bohr model, use orbits like planets around the sun. Now we're going for areas of probability, and those are orbitals. Okay, so we do have to recognize how far away these electrons are from the nucleus. That's going to be that's going to help us out with Coulomb's law. He does actually explain the momentum of an electron. We're not going to be as worried about that. And we will be worried, though, about the location. And so the stability region is going to be, we're going to learn that that's like 1s2 or 2s3, you know, those things. Another individual came along, Heisenberg, and said it's very difficult to come up with the same type of data you would be able to come up with if you're trying to figure out where Mars is located and how fast it's going. Or even the Bohr model about the electrons. And that's called the uncertainty principle. And that kind of lends itself very well to this idea of probability. So instead of trying to figure out where something is at, we're going to figure out where we think they are going to be. Okay, so this is kind of, some of this is stealing a little bit from the Bohr model. We have these energy states. So the Bohr model was distances away from the nucleus. The further away you get from the nucleus, the more energy that electron is going to possess. But again, we're going to call these orbitals because those are areas we think electrons are going to be. And we're not going to get into it very much in AP chemistry, but you can kind of come up with an address for every electron. And though that address, you know, the street number, the street, the zip code, all that for a house, we're going to use quantum numbers, or you could use quantum numbers for electrons. The only one that I think you should know by name is the principal quantum number. There's going to be 4 of these, and we're going to use probably some of these, and you're going to see where they're going to get used. But the principal quantum number is how much energy does the electron possess. And those, you're going to see those like as 1s. The 1 is designates that it's the closest you can get to the nucleus, as opposed to if you were in 4s, well, 4s is going to be much further away from the nucleus. But anyhow, that's principal quantum number. The orbital angular momentum quantum number is really these shapes. And you did learn these shapes last year. Someone way before us designated them as S, P, D, and F. After F, they start to go by actual just letters of the alphabet in sequence. And someone named these. I don't know who named those, but they looked at actual data, and someone said to someone else, hey, that looks like sharp, that looks like principal, that looks diffuse. And those names or those letters stuck. But for us, S, P, D, and F. The third quantum number is the orientation. And we learned that by using boxes. So maybe you ended up putting, now I'm going to kind of mix 2 up here with the magnetic quantum number with the next one, this electron spin. But you would have started to put electrons in there with these arrows. So the orientation is an up arrow, or is an arrow in one of these boxes, and then depending on which way the arrow is pointing would be the electron spin. Okay, and we're going to use some of these ideas, and you've used some of these ideas already in your first year chem class. So I showed you this already. So this one has actually some electrons already residing. So there's 2 electrons there. There's 2 electrons there. There's 2, 4, 6 there. There's 2 more. There's 6 more. And there's 1 more. So if I added all those electrons up, 2, 2, and 6 is 10. 2 and 6, that's 18, 19. This has 19 electrons. So if I looked on the periodic table, that would be potassium. So this is potassium's electron configuration. These electrons are closest to the nucleus. This electron is the furthest away from the nucleus. the further away you get from the nucleus, the more energy it possesses. And that's going to explain lots of things about potassium, how it reacts. Again, again, I don't teach this way, but you can use this diagonal method to kind of get an idea about memorizing the different parts of the electron configuration. Okay, so this is brand new, likely brand new for you. And we're going to get into this a little bit more later, but how do people know how much energy is required to get rid of electrons on different atoms? Well, there is a piece of machinery that can analyze that. And we're going to talk about this later. And this is very, very much cleaned up. This isn't how it would really look in the printout you would get on a computer or a piece of paper. But at a certain amount of energy, 151, you could get rid of the 2 electrons closest to the nucleus. How did I know those were close to the nucleus? Because I think it would make sense to you if an electron already has lots of energy, it doesn't take very much more energy to release it, meaning to get rid of it. These outer electrons, and how do I know those are outer electrons? It doesn't require hardly any energy to remove the 3p electron, 0.58. And remember that Coulomb's law was Q1, Q2, that's the charge of maybe the proton, the nucleus, the charge of an electron, divided by, I think we had r squared, but we could have put r there. R is the distance away from the nucleus. So the more distance away from the nucleus, the less attraction there is. So if there's less attraction, it's not going to take very much energy for that electron to get spit away. That would be kind of like, again, on your refrigerator and a magnet. If you have lots of pieces of paper between the magnet and the refrigerator, it would not take very much effort for that magnet to get popped off. If there wasn't anything between the magnet and the refrigerator, it would take a tremendous amount of energy for that magnet to get popped off. So what is this? This is not really, these are 2 different graphs. One is experimental, and then one is taking experimental data and just putting it into like a spreadsheet kind of graph. But IE1 means ionization 1. How much energy is required to get rid of 1 electron? This is to get rid of the 2nd electron, and then the 3rd, and the 4th, and so forth. And if you notice, let's just look at one of these. Sodium, it doesn't take much to get rid of the 1st electron of sodium. And you may have learned that sodium loves to get rid of 1 electron if it had a mind of its own. But to get rid of a 2nd electron, and we're going to have to figure out why that is, it takes a tremendous amount of energy. If you look at magnesium, for some, so let's put a little divider there. It's easy to lose 1 electron from sodium. It's super hard to lose a 2nd. With magnesium, 735, not crazy. 1445, that's double. But then there's a tremendous jump from 1445 to 7,730. And you'll find that all these have a gigantic jump somewhere. And we're going to have to figure out why that is true. And maybe some of you already have figured that out, but we'll get that. Probably not today. I think it'll be with the next notes. Okay, so we already talked about electron configuration. This is sort of like the address of the electrons. You could use orbital diagrams. That would be, I think for you guys, that would be like the boxes, okay? I think somewhere else in this they've used circles, but it's I think boxes might be a little bit easier. And then there's roles. There's 3 roles actually. One is Pauli exclusion principle. One's Hund's rule, And we have another one called the Aufbau principle. So Pauli exclusion principle says that you can't have two electrons with the exact same configuration. And what that really means is you can't have two electrons doing that. That is a no-no. Because if you had two electrons doing that, they would actually repel each other. Electrons are negatively charged, so one would do that, and then the other one would do that. That's the correct method. This is new, probably. So I attach this to Pauli exclusion principle. You can have times where you could have lots of unpaired electrons, and they actually have some ability to act a little like, or be attracted by a magnet. And then there are other times where you have diamagnetic, which doesn't have any ability to attract or repel a magnet. So where would you see this happen? Maybe that in the electron configuration, it ends in that. So that would be able to be attracted by a magnet, as opposed to maybe another time you have that. You wouldn't be able to attract a magnet with that. Okay, so this will probably be one multiple choice question on the test. So it's not a big deal, but it's still going to be probably on the test. Hund's rule. It might be easier for me to show Hund's rule, but you can read that. So Hund's rule is you have to put one electron in a box in one of these orbitals, suborbitals, before you double up. Okay, so this would be good. That would be bad. That one of these electrons in this first box would have to go into that second box. And think about if you had a box and you had a bunch of ping pong balls. If you put a ping pong ball in the box, it's going to sit at the bottom. If you put a second ping pong ball in the box, it's going to sit at the bottom. It's not going to stack up. And that's sort of the idea. It's going to go to its most stable location. And being right there is not very stable. Okay, and I mentioned that your third rule was going to be Aufbau principle, and that is just the electrons residing closest to the nucleus all the way out to infinity. We're not going to go to infinity, but as you go further out, these electrons have more and more and more energy. The ones close to the nucleus possess the least energy. And we are going to talk about this thing called the shielding effect. And what that means is all these electrons get in the way of these electrons and the nucleus. And that's kind of like having all those pieces of paper between the magnet and the refrigerator. So these electrons way out here are not very attracted to the nucleus, meaning that you could pull those away very easily. And the further out you get, the easier they are to pull away. You've already learned about the valence electrons last year, and we consider the outer electrons to be like 2 for helium or hydrogen to get there, or for everything else 8. And we usually consider that if you had S2P6, 2 plus 6 equals 8 electrons. That would be the octet rule. And everything follows the octet rule. Almost everything follows the octet rule. There's a couple that follow the duet rule, and they just have to get the 2. So like helium, for example, is a noble gas. It satisfies the duet rule. It ends in 1s2. And we consider that to have a full valence shell. So let's see what we got here. debating quantum theory at the ultimate science party. So many of the individuals that we discussed today are actually in this picture. I know we didn't discuss Planck yet, but we also didn't discuss Curie, but you might know her. Oh, we didn't talk about Einstein either. Actually, there's another one we didn't mention yet, de Broglie. We did mention Bohr. We mentioned Heisenberg. We mentioned Pauli. We mentioned Schrodinger. I think that might be it for the ones we've gotten to. But that just puts maybe some faces to the names. Again, we've talked about this diagonal rule many times here so far, but 1s2, then 2s2, and you can keep on going. But I don't really like to use that. I just like to, I think of, by the way, if you go to that, I think that would get us to about 99% of all the AP chemistry questions you would need. I don't think you're going to have to go past that. Okay, so I promised that we would talk about these diagrams. So, by the way, it's called photoelectron spectroscopy. No one calls it that. People just call it PES. And this piece of analysis is you bombard atoms with high energy, and as you give it more energy, you would be able to spit off more and more and more electrons. You have to be very careful by looking at these numbers. This is one graph. It's just too long to be able to put it lengthwise, so they separate it into 3 parts. And it looks like that's the highest energy, and it looks like that's the lowest energy. These don't all go from 0 all the way out to 500. Some of them start at 500 and work their way to 0. You just have to be very careful to make sure you check that out. And if you would give this no energy, no electrons get spit out. But if you give this sample 0.74 energy, of course, we don't even know what this energy unit is. It doesn't matter. It's all relative. You would be able to spit out 2 electrons. How do I know it's 2 electrons? Because this hump goes to a certain place. Okay. And I know electrons can, orbitals can hold, suborbitals can hold 2. There's other orbitals that can hold 6. There's other orbitals that can hold 10. There's other orbitals that can hold 14. So that still doesn't tell me it's 2, other than someone wrote down 2 there. But this hump here and this hump here is a ratio of 1 to 3 from each other. So that's how they knew that this one was going to have 6 electrons. And by the way, you need more energy to spit those electrons out. And remember I said that the further away you get from the nucleus, the easier it is to lose electrons. So these electrons are the valence electrons. They're the furthest away from the nucleus. These, as opposed to these, electrons are closest to the nucleus. We can call those core electrons. So it takes a tremendous amount of energy to get rid of those. Why? Because Coulomb's law, not Q, but R. R is the distance away from the electrons to the nucleus. And these electrons right here are ridiculously, well, they can't get any closer to the nucleus. So that R, I think I gave you R squared, but that R number is going to be tiny. So if that's tiny, the Coulomb's attraction is going to be the largest. Okay. Let me erase some of these. Actually, let me erase all these. Okay, and how did they know it was magnesium? So 2, 6, 2, and 2 adds up to 12. And if I look on the periodic table, the 12th atom on the periodic table is magnesium. And what else can we determine? This is 1s2, closest to the nucleus. Then we have 2s2. That's the next on the off-belt principle, because those have the next amount of most amount of energy. 2p6, 3s2. Okay, and we'll definitely have to practice those a little bit more. Okay, so this is, it titles this as lithium. How do we know it's lithium? Well, 1 electron, 2 electrons equal 3 electrons. The third element of the periodic table is lithium. Which electrons are which? These are the 1s2, and this would be 2s1. Do you see that this and this are half of each other or double each other, depending on which way you're looking? They won't always have the 1s and 2s up there. Let's practice that again. Identify the element represented. Okay, so again, they did give us some numbers. So you got 2, and you got 1. That equals 5 electrons. Fifth element on the periodic table is boron. This would be 1s2, 2s2, 2p1. Can you translate all these? These are all magnesium. Well, that one's super easy. 2, 2, 6, and 2. That's magnesium. Now, here's one that doesn't give you the numbers. This is 1s2, 2s2, 2p6, 3s2. How did I know it was in that way? The most energy are the closest to the nucleus electrons, and the least energy is the electrons furthest away from the atom. And how did I know how many electrons they have? By looking at the heights. So it does help you out that you can kind of see that this is, they don't always give you these lines either, but there's 6 lines there, so you can kind of gauge the heights of those by just counting up. So again, closest to nucleus, most energy. Furthest away from the nucleus, the least energy. Oh, here's another way. This is the Bohr model. Again, the Bohr model is very convenient because we can write that 2-dimensionally. And here is the box orbital diagram over here. Yes, they use circles, but you could have used boxes too. Okay, so again, the PES diagrams were able to give you these numbers. What's the lowest number on this list? Oh, right here. It requires only 5.21, whatever that voltage is. We'll just call it energy. 5.21 energies to get rid of 1 electron of sodium. What else has a small number? Lithium has a small number there. And we'll have to figure out why that's true. But maybe if we look at sodium's electron configuration, 1s2, 2s2, 2p6, 3s1. To get rid of that 1 electron doesn't require much energy. I got my phone ringing here. I think it is a crank call. Okay, so I think this is our last thing we're going to do is write electron configurations. Magnesium. And by the way, if we do one of these, we can. This really kind of translates to all these. Maybe we'll do argon. Z, by the way, is the charge of the nucleus, meaning that it's the protons. Why is that important? Because whatever protons you have, that's how many electrons. So protons equal 18. That means electrons equal 18. So we start off at the very lowest point. I'm going to end up writing it a little above here. 1s2, 2 electrons. Then 2s2, 2p6. So I think we've accounted for 10 electrons so far. Then we go to 3s2, 3p6. And I think that adds up to 18 electrons. And then if you were going to do the orbital diagrams, you just have to add in the boxes. Remember that S's have one box, can hold 2 electrons. P's have 3 boxes, and they can hold 3 electrons. I'm just doing half arrows. That's fairly typical there. And then 3s2. And then lastly, 3p, 1, 2, 3, 4, 5, 6. And that would be, again, argons. But you could do these other two just as easily, just that this one, magnesium only has 12 and phosphorus only has 15. I thought that was last, but no, the last is we're going to use the ideas about Aufbau, Pauli, and Hund to see if there's anything wrong with these. 2 electrons in a box without electrons in the others. So that's what we have is this. Does that violate a rule? Yes. Hund's rule. You are supposed to do that instead. Is there any violation here? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Ooh, this isn't the place where you're supposed to reside, or where electrons are going to reside next. I think it's supposed to be, well, let's see. 1s2, 2s2, 2p6, 3s2, 3p6. No, that's the right spot. That's weird that it happens like that, but that's how it goes. Next, by the way, if we had to put more electrons, would be in the 4p. But this does not ruin any of our rules. So we are A-OK with that one. 1s2, 2s2, 2p6, 4s. Ooh, now that's an issue. You aren't allowed to go into 4s until after. So the 4s is supposed to be out there. So this is an Aufbau principle problem. Let's see what else we got. We may have a couple more of those. Okay, so this looks like the same problem, but it's not the same problem. It's supposed to go 1s2, 2s1, but these this one electron here jumps way out into the 4s1. That's okay. That's just called excited. That's an excited electron. It's not a violation. No rule was broken. It'll eventually fall back down, and remember, when it falls back down, it's going to release energy in the form of light. So that's a tricky one. 2 electrons in the same box with same arrow direction. So that is this. I think that's a Pauli issue. It's supposed to be that way. Yep, I think we're done. Okay, so that gets you some of our review from last year, and then also I think we added a few new things this year.